Welcome back. So, as you can always see that I have drawn a surface, and at a point ABC on the surface, in space, I have drawn a tangent line. Okay, and yesterday we have already worked it out that the equation of the tangent line at the point ABC is given by your z minus c. This is equal to fx at AB, your x minus a plus fy at AB, your y minus b. Okay, let me call this equation as 1. Okay, fine. Now, one thing I would like to tell you is that, I mean, in order for the tangent plane to exist, these first order partial derivatives, fx and fy at AB, remember, they must be continuous. Okay, otherwise we won't be able to draw the tangent. We'll see it later on. Okay, and another thing, yesterday I was telling you about, I mean, the normal. Suppose I'm drawing a normal to the tangent line at that point, and we have already seen. I mean, while comparing this equation with the equation something like, say, your a x minus a plus b, y minus b plus c, y minus c equal to 0, where your ABC, they are
Z minus c.
Z minus c, yes. Thank you. Z minus c equal to 0. So while this capital A, B, C, they are the components of the normal. So then, if from yesterday's class itself, it was obvious that this was simply your fx, the components fy at AB, and then minus 1. Okay, then minus 1. Okay. So now, let me tell you one thing. Whenever you think about, let me erase maybe this one. Okay. Whenever I think about the surface, and whenever I think about a normal at a point to the surface. Okay. So now, depending upon the orientation of the surface, I can define this normal to be inward or outward. Okay. So now let me consider an arbitrary vector in space. So suppose I am considering an arbitrary vector. Okay, fine. And if I want to find out the orientation of this vector, so basically what I would be interested in, whether this vector, it is going to lie above your xy plane, or like, say, that means its orientation will be upward like this, or if it is going to lie below your orientation is going to be in the downward direction. It is going to depend upon if the components of this vector, suppose they are simply, say, PQR. The components of this vector is, say, PQR. So remember, if R is positive, then how you are going to draw the vector? So PQR, I mean, then you are going to move along x-axis, you are going to move along y-axis, and then you are going to move along z-axis, isn't it? Right? So you will see that if the z component is, basically the third component is positive, you are always going to get a vector which has an upward direction above xy axis. Okay? Similarly, if it is negative, it is going to have a downward direction. Okay? So now, obviously, the way we have found out this normal here, because this is -1, you will see that its direction is going to be downwards to the xy plane. Is it okay? Fine. So
Yes.
yesterday I had shown you a figure. I'll try to come back to that. So over there, while they were depicting this normal, they were writing it as minus n. They were depicting it as minus n. Okay, so the way I have drawn the figure, like it seems that the outer normal here, it has orientation above, x right here. Okay, fine. So that is why the third component must be positive. So that is why they were taking that to be minus n. But you guys needn't worry about that. Okay, let me tell you. And again, here I am not going to call it an outward normal. Okay, arbitrarily, I am not going to call a normal and outward normal if the third component, is positive. It is not like that. It is going to depend upon this surface. Okay, let me tell you why I am. And again, see this this fx AB, fy AB, and minus 1, right? I have these three components of the normal when I compare the equation of the tangent plane and the components of the normal. I found it like that. Now, if I want to make this positive, then what I have to do? I have to make these two negative, right? So then what is going to happen? Like earlier, what we did? I had, like, say, it is something like fx AB x minus a plus fy AB y minus b, and then I had minus 1 into j minus c equal to 0, right? I can do the same. By making it plus and making these two minus, isn't it? I'm still going to get the equation of the tangent plane, isn't it? So then I am going to get these as the components of the normal, right? So now, just to illustrate the concept more clearly, let me tell you about this sphere. Okay, fine. So now, if you consider the upper hemisphere, then if you want to take a normal at a point on the surface of the sphere, right? So definitely here it will be outward. Isn't it? Now, if you consider a normal for the portion in the lower hemisphere, the outward direction is going to be like this, isn't it? So you can see that this is definitely going to have third component negative. This is going to have third component positive, right? But still they are outward normal. So this is an illustration where, in order to decide whether it is outward or inward, you will have to look at the what surface. Okay, fine. So basically, this is going to be something like z equal to minus square root x square minus this, and this part is going to be something like z equal to plus. It is going to be something like this. Okay, so now the concept of outward and inward normal should be clear. So basically, if this is outward normal, then the normal that we take in the direction opposite to this, so that is, if this is n, this is minus n, so that is going to be the inward normal. Okay, now here you can see that here the inward normal had what direction in the downward direction, right? But if I consider the inward normal at this point for this sphere, x square plus y square plus z square equal to a square, then you will see that here the inward normal is going to, if this is outward, this inward normal is going to have an upward direction. Okay, so basically the inward or outward, it is going to depend upon the surface. Okay, fine. So now let me show you some commonly used surfaces, and after that I will move to the concept of linear approximation or tangent plane approximation. So here are some commonly used surfaces. Okay. So this one, so this is R. You should remember R is simply square root x squared plus y squared. Okay. So here you can see that this is a cone. So if you take the cone of xy plane, so that is going to be designated by j equal to square root x squared plus y squared. And if you take it below xy plane, it is j equal to minus square root of x squared plus y squared. So similarly, this is the paraboloid. It's given by j equal. Just a minute. It's see. It is given by j equal to x squared plus y squared. Okay. And similarly, like if you consider an ellipsoid, it is going to have some equations like your x squared by x squared or a squared, x squared by a squared plus y squared by b squared plus j squared by c squared equal to 1. So I have just shown you the figures because these are some very commonly used surfaces, and we are going to make use of them quite frequently later on. Okay. So now the next thing is very important. Next thing is about linear approximation or tangent plane approximation. Okay. So firstly, I'm going to show you some figure. After that, I'm going to come back to your blackboard teaching. Okay. See here, what you can see. Now I'm trying to find out the tangent plane to the elliptic paraboloid given by j equals to 2x squared plus y squared at the point 1, 1, 3. So you can see the third, this coordinate j, it is nothing but 2 into 1 squared plus 1 squared if you plug in the values of x and y. Okay, fine. So now what you can see, this one is the surface 2x squared plus y squared. This is the graph of the function f of xy given by 2x squared plus y squared. Okay, and at this point, this is the tangent. Okay, fine. Sorry, tangent plane. So now what is being done here? I am moving towards the point, and in that way, what we are trying to do, we are magnifying this figure. So if I go closer to that point, you can see that the surface is looking more flatter, right? Even if we go further, you can see that the surface is even looking more flatter than the previous one, isn't it? Is it okay with you, everybody? Fine. See here you can see here the range of x and y. You can see it was from -4 to 4, -4 to 4. Here it is -2 to 2, -2 to 2. Here what they have done, they have simply shown 0 to 2, 0 to 2. Is it okay? So now it is getting flatter and flatter. So if you go again, if you magnify it further, say suppose you take the range of x and y from say maybe -0.5 to 1.5 in both the direction, then you will see that the tangent plane is almost overlapping the graph of this function, right? So what it is telling you, let me try to analyze this through the concept of linear approximation. I would like to come back to this figure again. And these are nothing but the contour map. So what they are doing, they are trying to slice this surface with some plane parallel to xy plane, and then they are plotting the contour lines, and you can see the contour lines there. Their curvature is decreasing as you are approaching that particular point. Okay, fine. So let me come back to this blackboard teaching now. Okay. So we have already learned about suppose I have a surface given by this. Okay. now, if I want to find out the tangent line to the surface at the point ABC, and of course this C is nothing but f of AB, right? So then the tangent line will be given by J minus C equal to Fx, this x minus A plus Fy AB y minus B. Okay, fine. Now, let me consider one example here. Okay, the same problem that I have shown you. Say z equal to 2x squared plus y squared, and suppose I'm trying to find the tangent line at the point 1, 1, 3. Okay, so then obviously from here this is going to be z minus 3, and you know that at 1, 1, I mean this zx or fx, this is what 4x, and zy, this is 2y, right? So at the point 1, 1, your fx or ab, this is simply going to be 4 into x minus 1, and then this is going to be 2 into y minus 1. So eventually I'm going to get j equal to 4x plus 2y. So this is going to be minus 4 minus 2, that is minus 6 plus 3. So this is minus 3. Okay, fine. So now let me define a new function. Say L of xy, which is given by this expression. Okay, so this is 4x plus 2y plus 3. Okay, so now say I have two functions.
It will be minus 3.
Minus 3, sorry, yes. Minus 2, right. So now what is happening? I have one original function given by this, and I have extracted another function out of that original function through the equation of the tangent line. Okay, fine. So now let us take a point which is very near to 1, 1. Say, suppose I am considering the point, say 1.1, 0.95. In fact, I have taken this example from Stewart. Okay, so then if I want to find out L at 1.1, and 95. So this is going to give me 4.4. 1.9 minus 3, right? So this is going to be 3.3. Okay, fine. And now if I want to find out your f of 1.1 comma 0.95, so let me tell you, it is going to be 3225. Just 3225. Okay. Now, if you look at this one and this one, they're very close to each other, isn't it? Is it okay? Fine.
Yes.
Now, suppose I want to find out, say, L maybe 23. L23 will be what? 4 2s are 8. 2 3 plus 6. 8 plus 6, 14.
8 plus 6. Yeah.
14 minus 3, it is 11, right? Now, if I want to find out f of 2, 3, so it is going to be 2 into 4, that is 8
Plus 9.
plus 9, right? 70. Okay. So now let us concentrate at these two. So what is happening? The values of the functions f and L, they were very close to each other. At the point 1.1, 0.95. But as what is happening as you are taking the point 23. In fact, the point 23, it was a bit away from the point 11. Then you can see that the difference between them, it is deviated, right? Is it okay? The observation? Are you comfortable with the
Yes.
observation? Right? So what does that tell you is that if I want to approximate a function given by some expression with the help of this new function, which is nothing but it has been obtained through the tangent line. So if I want to approximate the function with the help of this new function in the vicinity of the point at which the tangent line has been considered, then I get a very good approximation. Okay, but if I move away from the point at which the tangent line has been considered, then the values are going to deviate. It is no longer going to give you a good approximation. It is going to get worse and worse. Is it okay? Fine.
Yeah.
So this approach, it is called linearization. It is called linearization. Okay, and it is also called tangent line approximation. It is also called tangent line approximation. So basically, what I do, like say, whatever function I have, because see, this was 2x squared plus y squared, okay, and you may have something like higher powers of x and y. You may have a transcendental function, but eventually, if you consider the tangent plan to the surface, which is nothing but the graph of the function at a particular point, so then you are always going to get a linear function, isn't it? Right? Because x and y, they are always going to appear linear. So that is why it is called a linear approximation. Okay. So now let us again quickly browse through our slides. Then I'll come back again. Okay. So this is what we have done. The linear function of two variables L, X, Y is a good approximation to f of x, y when x, y is very near to 1. The function L is called the linearization of f at 1, 1, and this approximation. See here this Lxy, this has been written as fxy approximately equal to this. Okay, so this one is called the linear approximation or tangent line approximation of f at 1, 1. Okay, right? So this I have already told you the observation. Okay, so this is the formal definition. In general, we know from our earlier study that an equation of tangent line to the graph of the function f of two variables at the point a, b, f of a, it is, see here I was writing c here, right? They have written f of a, but I have already told you that c is nothing but f of a, b. So j equal to this. Okay, so this is the equation of the tangent line. The linear function whose graph is this tangent line, namely this one, is called the linearization of f at the point a, b, and this approximation is called the linear approximation or tangent line approximation of f at b. Okay, fine. So you may be thinking, what is the need for this? What is the need for this? So basically, what we are getting a very simple function, that is L of xy out of baby. Although the example I have taken f of xy, that is 2x squared plus y squared, it was not very complicated, not very cumbersome function to work out. Sometimes you may have some very cumbersome function to work out. So in that case, if you are interested in simply approximating the function at certain points, so what you can do, you can simply consider the tangent line there. So you get a much simpler function and you can approximate. So now the $1 million question is, is it the, only thing that we are interested in, right? Why we are doing this? Okay, so I'm going to pose it. Now, suppose f is not continuous at AB, and even if f is continuous at AB, even then still may be some issue. Like say, is the tangent line always guaranteed? Is the tangent line always guaranteed? So obviously, if f is not continuous at AB, so then you won't be able to draw the tangent line. Okay. Even if it is continuous, then also we may have some issues. So we are going to think about this now. Okay. So now I'm don't look at the definition. Don't look at the definition of differentiability. I'll come back to that later on. But I would like you to have a look at this function f of xy equal to xy by x squared plus y squared. Okay. And then it is if it is if xy is not equal to 0, 0, and it is defined as 0 at the origin. So now this is the graph of the function, and of course you can see that the graph, the way it is. So obviously at the origin, drawing a tangent plan, it will be extremely difficult. Drawing a tangent line, it will be extremely difficult at the origin. So now let us try to make some more observation out of this function. Okay. Okay, fine. So this was our function. This was our function. Okay. So obviously, you can see that here I already know that limit xy, it doesn't exist, isn't it? It doesn't exist because I can take a very straightforward approach. Say if you want to approach the point 0, 0 through the line say y equal to mx, through the line y equal to mx. So then this limit is going to give you what? Limit x tends to 0, your m by 1 plus m squared, isn't it? Right? And for different values of m, you are going to get different values of this expression. Is it okay? Right?
Yes.
So that is why the limit doesn't exist. So since the limit doesn't exist, we are not even going to do all the other stuff. We can straightforwardly say that the function is not continuous at the origin. So is it only that? Now let us try to find out. Your partial derivative at 0, 0. Partial derivative of the function at 0, 0. Okay. So if I do it partial derivative with respect to x, that should be good enough for us to have an idea. So this is simply from the definition of partial derivative. So this is limit h tends to 0. So it is, this is 0, right? Yeah, fine. It is 0. So similarly, this is also going to be equal to 0. So obviously, even though the function is not continuous there, the partial derivatives at that point with respect to x and y, it exists. Okay, so that is an interesting observation here. So now, why I am doing all this? Why I am doing all this? So you may be thinking, okay, the partial derivatives are at those points, I mean, exist, right? So can we still draw the tangent at that point? Because from the figure that I have shown to you for the graph of the function, right? You can see that obviously at the point 0, 0, a tangent line is not possible. Okay, so now let us again, I mean, probe further. Let us again probe further. So now let us try to check whether those partial derivatives at those points, sorry, partial derivatives at the origin, it's continuous there or not. Okay. So now, obviously, if I want to find out, I mean, limit xy tends to 0, 0. This we will see that. Because at other points, I'll be able to find out the partial derivative here. So this is going to be what? This is going to be your x squared plus y squared whole squared. Then y into x squared plus y squared minus 2x xy. So basically, it is going to give me yx squared minus at the numerator. It is going to give me yx squared. No. And then this minus 2yx squared, right? So it is going to give me
minus x square
y cube minus x squared y.
Yes.
Okay, fine. So now again, if I take the approach, along your say, maybe I can take it along y-axis, I can take it along x-axis. So if I want to find out the limit along x-axis or say y-axis, so then it is going to be your x tends to 0 if I want to consider along y-axis, right? So then it is going to be what? Y cube by y to the power 4. So this is going to be equal to 1 by y. But again, see, what? Sorry, I should have written both problems. Okay, so here along y-axis, your x is exactly equal to 0. Okay, so then again, this doesn't exist, isn't it? As in when y tends to 0, this limit doesn't exist. Is it okay?
Yes, sir.
Fine. So similarly, if you want to find out limit xy tending to 0, 0, fy xy, so then also that is not going to exist. Okay. So what does that tell you? It tells you. Let me just close my window. Sorry. What does it tell you? What does it tell you? That your fx and fy, those partial derivatives, they are not continuous at the origin. Is it okay? Fine? Because
Yes.
for them to be continuous at the origin, what I must have, this must be equal to fx at 0. But since this limit itself doesn't exist, it is not continuous there. That means the first order partial derivatives are not continuous there. So, with all this information, I would like to come to the definition of differentiability. Okay, definition of differentiability. But before that, let me tell you is that for a function, if the partial derivatives exist at a point, say AB, say suppose I am considering a function f. If partial derivative of x and fy they exist at AB, and if they not only exist but they are continuous, we say that f is continuously differentiable. Okay, f is continuously differentiable. Now I will come to the definition of differentiability. I'll come to the definition of differentiability. Okay, fine. So so what we did say let me get back to this. Differentiability. Let me go back to say function of one variables. Function of one variable. Okay. So what did you do here? Like if I want to consider differentiability of a function y equal to f of x, say x equal to a, right? So then what we did, we defined your delta y to be equal to something like fine. Okay, so then I had defined f prime a is to be equal to limit delta x tending to 0, delta y delta x. Okay, and from there what I did delta y equal to f prime a delta x. So it is going to have some epsilon into delta x in such a way that epsilon tends to 0 as delta x tends to 0. Is it okay?
Yes.
Fine? Right? And if you have a close look at this, f prime a it was nothing but the slope of the tangent to the curve y equal to fx at the point a f, right? So from the the concept of differentiability of a function of one variable, we can also move to the differentiability of a function of two variables. So in case of a function of one variable, what we did, we were taking the tangent line approximation, whereas for a function of two variables, we are going to take the tangent line approximation. Okay, so let us get over it. So this differentiability of a function f at a is f at a. Okay, fine. So if I denote, I mean j equal to f of x1. So then, as before, your delta z, and if I consider increments, delta x and delta y along x and y directions, so then this is simply going to be a okay, fine. So as in the case of function of one variable, if I Now go to the tangent line approximation for a function of two variables. So the tangent plane would have been given by this expression. I'm going to change it, just for the time. Please hold on for it. Right? It would have been given to me by j minus. It would have been given to me by this, isn't it? Fine.
Yes, sir.
Yes.
Okay. Whereas for a function of one variable, it was given by say y minus fa, that is equal to f prime a x minus a, right? See, similarly it is given here. Okay, and then what we did, the differentiability we defined. So now instead of x, you can write a plus delta x. Okay, so this is going to change to delta x. Okay, and this is going to change to delta y. Okay, so now what we are going to do, as in case of a function of one variable, we are going to say that the function f is differentiable at the point AB if this happens. Delta z equal to delta y, then plus epsilon 1 delta x plus epsilon 2 delta x, sorry, epsilon 2 delta y, where epsilon 1, epsilon 2 tend to 0, as your delta x, delta y tend to 0, 0, tend to 0, 0 simultaneously, 0, 0. Okay, fine. So this is the definition of the differentiability of a function of two variables. Okay, fine. So now, obviously, from here, I can directly prove a theorem. I can directly prove a theorem. So, your from here, just yeah. So this is the definition of differentiability. Okay, so you know that your epsilon 1, epsilon 2 both tend to 0 as delta x, delta y tend to 0, right? So this is the definition of differentiability. Now, if delta x, delta y tend to 0, so obviously what is going to happen? The right hand side is going to tend to 0, isn't it?
Yes.
Right? So that means if I take limit delta x, delta y tend to 0, 0, f a plus delta x, b plus delta y. So that is going to simply give me f of a b, isn't it? So that means if a function is differentiable, then it must be continuous. Okay, fine. So I'm again going to show you some slides. Then I'm going to come back to. So these we have already worked out. Okay.
Sir,
What
slide
is
is not clear.
Pardon?
Slide is not clear.
In fact, I mean something is hiding it, right?
Yes.
Now it
Yes,
is
sir.
right? Yeah.
Not now.
Yeah. So now what is the value of the first order partial derivative at 0, 0? We have already worked it out for this particular function, right? And what about the linear approximation there? Can we do a linear approximation there? We cannot do that. We cannot do that. Okay, fine. So now this is the definition of differentiability of a function of two variables. I have already told you. And what about the value of the function along y equal to x? So see, basically what I did, when I was trying to check the continuity of this function, I was using y equal to mx. They are simply using y equal to x. So I got m by 1 plus m square. So you are going to get 1 by 1 plus 1 square. So that is half, right? So you don't need to bother about it. We have already done it in a generalized way. Okay. This we have already done. And now I'll try to do this exercise. I'll try to do this exercise. Okay. So this function has partial derivative at the origin, but not differentiable there. So this one I'll prove. After that, this example I'm going to leave it for you. You can try it at home because we would have enough experience after working out this example, and I'm going to make some comments. Okay, right? So, this was my function. Okay. Okay. So, what I will do, that reflection is still there, right?
Now it's fine.
Yeah. So what I'll do, obviously, I'll try to bring it to this form. Try to bring it to this form. Okay. So what I'm going to do, let us call delta x equal to x, delta y equal to k. I mean, you could have simply written delta x, delta y, that stuff. So this will reduce my blackboard writing. So then from there, so if I want to take the differentiability at the point 0, 0, right? So I'll have to consider f of your hk. You simply look at this. So this is basically 0 plus h, 0 plus k. Okay? So this is what it is. Minus f of 0, 0. And then your fx at 0, 0. Your h, that is nothing but delta x, plus fy at 0, 0, k, and then epsilon 1x plus epsilon 2k. Now, before moving further, let me tell you is that this function is of polynomial form, isn't it? Right? So obviously, this function is going to be continuous at 0, 0. Right? We don't need to bother about that. Okay. So now, if I want to find out the first order partial derivatives at 0, 0, so if I go back to definition, so this is simply going to give me h0 minus f 0, 0 by h. So then h0, this is 0, h to the power 1 by 3 whole cube, that is simply h. And f of 0, 0, it is definitely 0. So h by h. So this is going to be equal to 1. Right? Okay? So similarly, you will find out that fy at 0, 0, that is also equal to 1. I don't need to do this. So that is why from here I am going to get this is simply h to the power 1 by 3 k to the power 1 by 3 whole cube. This is 0. This is 1. So I am getting h plus k plus epsilon 1 h plus epsilon 2 k. And again, say the equality for a function to be differentiable, the equality is going to be valid when as what? When epsilon 1 and epsilon 2 they are going to tend to 0 as h and k simultaneously tends to 0, 0. Is it okay? Fine. So that is what we need to prove the differentiability of this function. Okay. So now let us see whether that happens or not. So from here you will see that this is simply h plus k 3 and then h plus k plus epsilon 2k. So these two cancels out. And then what I will try to do, I will try to adjust these two terms in this form. Okay. So then what is going to happen? Say what I am going to do, if I multiply it by h to the power 1 by 3, so then this is going to become simply h. So if I do like is it okay, the adjustment?
Yes.
Okay.
Yes.
So for this to be valid, what must happen? So that means epsilon 1 must be equal to 3 into k h to the power 1 by 3, epsilon 2, 3 h by k to the power 1 by 3, right? So if the function is to be differentiable at the point 0, 0, what must happen? Epsilon 1, epsilon 2 must tend to 0 as hk tend to 0, 0 simultaneously. Is that happening here? If h and k tend to both tend to 0, 0 simultaneously, epsilon 1 and epsilon 2 is not defined. Isn't it?
Yes.
Yes. Right? So that is why the given function is not differentiable at the origin. Although the interesting thing here is that although both the partial derivatives existed at the point 0, 0, but still why it didn't happen. So you can easily check at home is that those partial derivatives, they are not continuous at the origin. Hopefully, I think they are not going to be continuous. Yes, you please check that at home. Okay, so I am going to make some observation here. I'm going to make some observation here. And in my next slide, there are going to be some questions. So, like say, why on the specific points we calculate partial derivatives for definition. So, there are some, as I have already told you earlier, that for example, I mean at 0, 0, if you want to, calculate the partial derivative simply by differentiating the original function, that may not be correct because we are talking about this incremental change there at 0, 0, which is a very sensible point. Okay, fine. So it makes sense sometimes if you, find out the partial derivative at certain points from definition. Okay, fine. And I'm again going to give you a formal definition of differentiability for a function of more than 2 variables. Okay. I was gone for a while, right?
Yes.
Yeah. So yes. Okay. At 12, something happens in my computer. Okay. See, if I consider a function of more than two variables, and if as I told you, I think yesterday or day before yesterday in my earlier classes, so we can define the limit in terms of limit or partial derivative, all these kind of things in terms of vector also. So for a function of n variables, if you consider the differentiability of the function at a point A. So A is nothing but the point given by the vector a1, a2, up to an. Okay, fine. And this it is a small, increment again that in terms of the vector. So this is again going to be vector having component h1, h2 up to hn, and C it is going to have component c1, c2 up to cn, and it is a constant vector. Okay, so this is the definition of a function of more than two variables. Okay, if you want to see the differentiability. Okay, so but we will be interested in a function of two variables only for the time being. Okay, fine. So now this particular example is it is interesting because here, as I have told you, that in the earlier example, the given function was not continuously differentiable because the first order partial derivatives were not continuous at the ODC. Okay, so and remember that is a prerequisite. Okay, so that sorry, no, sorry. That is not a prerequisite. What is happening here? If there's a theorem, I'm not going to prove it. There's a theorem. If a function is continuously differentiable, it is differentiable. But the converse is not necessarily true. And that is going to be exemplified by this particular example. You can change it. Okay. So this is the theorem, as I have told you. If the partial derivatives of fx and fy exist near AB and are continuous at AB, then f is differentiable at AB. Remember, this is simply a sufficient condition. Okay, and this you can try at home. Okay, and again, this function is not continuously differentiable at the origin, but you can check that this is in fact differentiable. Okay, fine. And these are the conclusions that if f is continuously differentiable, then f is differentiable. If f is differentiable, then all partial derivatives of f exist. And if f is differentiable, it is continuous. So these three observations we can make. So in my next class, I am going to tell you about differential, for that matter, total differential. Okay, so firstly I'm going to do it for function of one variable, and then I'll move to function of two variables, and that is going to help us in doing chain rule for a function of two variables. Okay, so that is what we are going to do. Okay, so then I will end my class at that note. So I'll again see you tomorrow. Okay? Thank you.